This is our final lecture for this week on scientific realism, week 4. Uh, this is a realist account of science called Structural Realism. You should have read the article by Worrell, and he thinks that his account can capture sort of the best of both realism and empiricism. So again, a little background to sort of walk you through the article. Uh, so as we have noticed, right, scientific theories posit all kinds of stuff that we can't see and can't be totally sure is there. So a curved space-time, right? So here in the picture we see sort of a sort of graphical depiction of space-time being curved around a massive object, there the Earth. Um, these fundamental physical particles like bosons, right, that no one can actually see, um, but that seem to make our theories work out, right, make the right predictions. And then we've got forces like gravity and magnetism, which at this point are very familiar to us, but again, no one has seen gravity, right? We see its effects. Um, so what we actually observe, right, again, the emotions of objects, right, under the influence of these forces, we do see tracks in cloud chambers that look to have been made by some of these fundamental particles. But even really even on the most liberal conception of observable, maybe you want to say, well, a track in a cloud chamber counts as seeing an electron, but scientific theories just are not the sort of stuff, right, that they get into, like string theory and things like that. They're like multi-dimensional, like right, it's 16 dimensions or something they exist in. There's just no way we're going to actually observe things like that in any sense of observable, right? Um, But even so, a lot of people say we still have good reason to believe that these unobservable things exist, right? Because uh, our theories are so good at what they predict, right? And that's good enough reason to think that they are true, right? So this, according to Worrell, is scientific realism, right? It's that our theories are true and the things that they posit exist. So notice a slightly different definition than what von Frosten did. Everyone has their own definition. But they're sort of cluster around the same notion, right? That our scientific theories are true, and these unobservable um, objects that they posit actually exist. And of course, we've seen a couple instrumentalist views, right? Empiricist view, we call them, logical empiricism. So that's the view that scientific theories don't literally claim that electrons exist, right? Instead, you're supposed to translate the word electron into an observable equivalent, right? So what, according to the logical empiricist, what scientific theories mean to say is that under certain conditions, we will observe certain things, right? So those don't entail any commitment to like the literal truth of curved space-time and stuff like that. And we've seen constructive empiricism in the last lecture. Now, according to this theory, the scientific theories are meant literally. They're not, they don't say, right, they're saying scientists don't mean by electron observation in the cloud chamber. They mean electron, the object that they're picking out, right? Um, but nonetheless, constructive empiricists say, um, but we shouldn't go along with them and agree that they're actually true, right? We should only agree that about the observable consequences, right? Again, constructive empiricism says the aim of science is not truth. Right? It's only empirical adequacy. And if I want to accept scientific theory, I don't need to believe that it's literally true. I only need to believe that it's empirically adequate. Okay, so that's just a little review. But what Worrell wants to do, I think both views have something going for them, right? And then both have problems, and he wants to try to unite them and get a view that has the benefits of both. And again, he repeats sort of the no miracles argument, which he thinks is the best argument for realism, right? Um, so it's so impressive, right? What science can do. We've talked about as the success of science, right? Um, quantum mechanics has been lauded as like the most successful theory in terms of its predictions, right? It makes incredibly accurate predictions, um, and you have to think that would just be an insane coincidence, right? If it got everything right but wasn't latching on to any truth about the universe. Now, of course, um, as Loudon pointed out, that's only a good argument if you're not sort of just constructing a theory based on the predictions that you want to make true, right? There's a difference between sort of predicting beforehand and everyone being impressed that it turned out to be true, and sort of knowing what you want to predict and sort of like gerrymandering a theory that'll give that prediction. Um, so this was shown, right? Loudon argued that this is a problem for the no miracles argument itself, which appears to maybe doing a bit of this, maybe be a bit of this gerrymandering, right? It's not really making, the no miracles argument isn't making any sort of bold new predictions that we don't know how they're going to turn out, right? It's taking the science, the success of science, and then sort of reverse engineering a theory that would predict it. So you may think that no miracles argument in some sense is very impressive, but then in another sense, um, uh, you might doubt it. And then the best argument against realism typically is taken from the history of science, right? And the phenomenon of scientific revolutions. We have these theories like Newton's uh, theory of mechanics that was so successful. Like for decades and centuries, people thought this is it, right? We know we have the answers to the universe, um, and they were convinced, like implicitly, by this no miracles argument. How could Newton get all this right, make all these predictions, and if it wasn't true? And then turns out it's not true, right? So even our best theories that everyone in the world is like, oh, this is it. Sure enough, right? Down the road, someone's going to figure out that there was something wrong with it, and we're going to come up with a better theory. This just seems to be how science goes over the centuries. Um, and Worrell wants to sort of like put a pin in this point. Pardon me. Right? Realists want to say that oh, Newton's mechanics is still true, right? It's just a limiting case, a special case of relativity, right? It's true. It applies to objects that are at a relatively slow speed, right? Relatively small, so on, compared to like galaxies and universes and stuff. And Worrell wants to put his foot down and say, no, no, no. Newtonian mechanics and relativity are literally incompatible, right? When Newton talks about mass, talking about a different thing than Einstein is. Okay, so how do realists usually deal with this fact that our theories change over time? Um, what they want to say, and Loudon discussed this as well, is that when he talked about convergent, right, realism, is they want to say scientific progress is essentially cumulative. So the new theories are going to keep the best parts of the old theories, the true parts, they're going to expand on them, they're going to revise them. And again, the realist likes to point to the Newton-Einstein thing and say, look, it was, Newton got it right for a certain sort of segment of the universe, and then Einstein just expanded it to bigger objects and faster objects. Um, what Worrell wants to say, really, if you look at more broadly at the history of science, you're going to see that scientific change is actually much more radical, right? Probably a lot most of the time. Take, for example, our theories of light, right? Um, so in the upper left there, uh, we have light as waves in a luminiferous ether, right? Some sort of substance in which the waves propagate. Um, Before that, it was a particle theory, like Newton thought that right, light was just little particles. Everything was sort of billiard balls bouncing around in the universe for Newton. Um, Now we get rid of the particles, we go to waves in an ether, then we go from waves in an ether to on the bottom here, electromagnetic waves, right? So all of a sudden, sort of radio waves and light um, and X-rays are all sort of the same sort of thing. They're just on a spectrum. Um, these seem to be very radical changes, right? Which is it? Is light a particle? Is it a mechanical wave, or is it something else, an electromagnetic wave? These are not compatible things. Pretty radical changes in the way we conceive of light. And Worrell describes this, right? He says the difference between a particle and a wave is like the difference between chalk and cheese. There's just no way to view them as the same sort of thing. Um, and it's not just our conception of the nature of light that changed, right? The entire theory changes along with it. So um, when I say light's a particle, I'm going to use certain kinds of equations to describe its behavior. When I say it's a wave, total different set of concepts and equations, right? Now, when I'm talking about a wave, I have to talk about interference, diffraction, polarization, all kinds of stuff that doesn't really apply to particles. And then when you change it to electromagnetic theory, now you've got a whole other set of theorems, right, that are relevant to electricity and magnetism that weren't involved in viewing light as just a wave propagating through a mechanical medium. So every time you change your essential notion of what light is, you also change all of the sort of associated um, right equipment and equations and theory. So looking at that history, right, of our successive theories of light, how could you say that that's essentially cumulative, right? That we're just like we're keeping the particle theory, but we're just getting better and better. He says, no, that can't be the case. But Worrell does want to say there is some kind of continuity, and this is empirical continuity. So empirical, again, is just sort of the same thing that von Frosten was talking about, right? The observable consequences of the theory, the predictions of the theory. And at that empirical level, the theory change does actually seem continuous, right? So the new theories, they want to save all the earlier predictions that were right of the old theory, and they want to make even new, better predictions, right? The old theory probably made a couple predictions that were wrong, so they want to fix those, keep the good stuff, keep moving forward. And that does seem to be sort of continuous, right? We don't all of a sudden have the new theory making all sorts of new right predictions, but then making the wrong predictions that the old theory was getting right. That's not how it works. So if you think that's right, if you like that, you can stop there, just be an empirical or an empiricist like von Frosten. You could even go with what he calls conjectural realism, which you say, well, science isn't currently true, but it's gonna be true someday. Um, but the problem is none of these really make very good sense of the no miracles argument, right? Which he, on some level, he thinks is convincing, right? They don't explain the success of science, right? So again, if you're just focused on the observable result, you're saying, I don't care, right, what the theory is actually trying to describe and how that relates to its success. They just look at the success, right? Um, and that should seem unsatisfying, right? You should say the science is successful because it's describing the things right, right? The observable consequences are the result of something else. It seems sort of like incomplete to only think about the observable consequences and just say, I don't even want to talk about electrons. I don't want to know about them, right? Then conjectural realism, right, is also problematic because what you're literally saying is our scientific theories right now aren't true and they're not getting at the truth. And so that doesn't help us understand the success either. So neither really does what the no miracles argument is asking us to do, which is explain why science is so good. So Worrell thinks he can get the best of both worlds, right? So he notices that even though scientific theories seem to change radically, right? The example being our theories of light, he does notice that the empirical consequences are continuous, right? We keep the good predictions from the old theory, we make more good predictions and more good predictions. And he wants to say there's something else that's also continuous across theory change. Um, some people say it's the causal relations, right? That is still sort of somehow being captured by all these theories. Um, and that's interesting, but it also feels a little weird, right? So how does it make sense to say that the causal relations, right, among when light is conceived as a particle is the same sort of causal relation that a wave could have, right? If you have different types of entities, aren't you going to have different types of causal relations? Um, it's sort of like thinking of like the causal relations between pool balls continue to exist without the pool balls, right? When you replace them with waves or something. Um, but Worrell wants to make a sort of a more plausible account that's sort of like this, right? Capturing these relations while getting rid of the what we say is the relata, right? So he does want an account that says Yeah, there is something right about the way the old theories and the new theories describe relations among objects, even if the new theory talks about totally different types of objects. So before he dives into it, he wants to talk about mature scientific theories. And we have discussed this, right? So realists want to help themselves out a little bit by only committing to the truth of mature scientific theories, right? So they're not saying that, I don't know, Aristotelian um, astronomy was like totally right. They want to be able to carve off some of the really old, really false theories and say, I'm not saying those ones are true, right? Just the more mature ones. But even, of course, among the mature ones, there is theory change and stuff. They do have to account for that, but they don't want to have to account for all of our change in theories from like believing that river gods sort of made people pregnant, right, to now, right? They want to say, okay, some of those old ones are false. They're not mature. Um, and Worrell says, fair enough. And actually, that'll help me out too. Um, so to be a mature theory, right, it's not enough to just make true predictions. Again, those can always be engineered post hoc, right? A mature theory is going to be one that makes surprising predictions, right? That we don't know if they're true, and we test them and they turn out to be true, right? So what Worrell then wants to commit to being real, right? His realism is going to apply to mature theories, right? And mature theories, again, he defines as ones that make new, surprising predictions. And so this is then a smaller subset of theories that he's going to argue are true. But even so, right, there is theory change even in these mature sciences, right? So we do have to account for what it is that is continuous, right, through all of these seemingly still fairly radical changes. Um, he says, okay, let's talk about light, right? Let's talk about the theory of light as a wave in the mechanical ether. Um, it was successful, right? Predicting, among other things, right, certain patterns that you would see, um, right? If you send light through a slit, if it's just a particle, it should just shoot right through, and you shouldn't see anything surprising. But if it's a wave, right, you're going to see very interesting interference patterns, right? And this is what these wave theories, even the primitive ones, thought it was in a mechanical medium, did predict, right? You'll see certain bright spots if you get them to waves to interfere. Um, in certain ways. Okay, um, so when we got rid of the mechanical ether, um, we still had this prediction, right? And we still wanted to make our electromagnetic theory of light um, also predict the same thing, right? Um, but there's something even more that's continuous between the theories, not just the predictions. Um, and what Worrell wants to say is it's the structure, right, or the form. And here's a nice quote. So he says, the field in no clear sense, and by field he means electromagnetic field, in no clear sense approximates the ether, that supposed mechanical um, substance that light flowed through. He says, but disturbances in it do obey formally similar laws to those obeyed by the elastic disturbances in a mechanical medium. So although Fresnel was quite wrong about what oscillates, he was, from this later point of view, right not just about the optical phenomena, right, so the predictions that you would see, but right also that these phenomena depend on the oscillations of something or other at right angles to the light, right? So he, again, ether got right the predictions about the sort of visible phenomena you see, right, because it's a wave. Um, and they were wrong about what it was a wave in, but they were right that it was a wave. It was an oscillation of something, right? And if we stick to the mathematical equations that they use to describe the wave's behavior in the ether, we'll find they're very similar or the same to the equations that were used to describe the wave in electromagnetic, right? An electromagnetic wave. Um, so what Worrell wants to say, his big insight is, we can be realists about what the equations capture, right? And the equations are capturing some sort of structure in the world. Um, Not necessarily the entities themselves, right? But the relations between them, in a sense, right? Um, And then we can accept this sort of limiting case view, where the newer theories do explain more phenomena, they make more predictions, the equations change, but the old equations then can be seen as a limiting case of the later ones if we're not worrying about objects they're positing, but we're only talking about the structure, the relations, right, between them, the things the equations describe. So even though there's no way to interpret Newton saw space as just sort of a container, right? Not as something that could be curved like space-time. But nonetheless, his equations do fall out of Einstein's equations if you plug in certain parameters, right, about the velocity of the objects and their size and things like that, their mass. So from a structural realist view, then the older theories, like Newtonian mechanics, are limiting cases of the later theories, right? If we ignore the the objects they're positing or the nature of mass and things like that, and just pay attention to the structure, pay attention to the equations. Okay, so that is structural realism. Again, it's realism about structure it's kind of most concretely sort of evidenced by the sorts of equations we use to describe the phenomena and that are used to make the predictions. Now, there are a couple different kinds of structural realism, what we call epistemic versus ontic. So go back to Dirac, right, and his sea of negative energy electrons. Um, uh, we don't believe in that sea of negative charge anymore. Our theories have moved on, but we still use his equations, right? Um, now, this part will be controversial, and again, maybe you could get into this for a paper, although you might have to understand the math a bit. Maybe if any of you are well versed in physics. Um, People might push back on this claim of the structural realist that we are using the same equations. Some people would say that actually, on the best interpretation, that the equations are fundamentally different. So that point just being that there's still argument about this stuff going on, right? But that is meant to sort of wrap up. I've tried to sort of replicate what Staley does in his chapters that you've hopefully read, was sort of using this sea of negative electrons posited by Dirac as sort of an example that we can trace through all the different views on what you might think about, right? That concept. Is he getting at something real in the world because he makes great predictions and it's simple and beautiful? Or is it something so insanely unobservable, right? It's not even like an electron, or at least you can see its path through something. Um, Although it did predict, right, the positron. But anyways, is it something that's so unobservable that you can't ever reliably commit to its truth, right? Or is it something that actually, now that we don't, that theory has been sort of bypassed and we're on to new theories, can we say that at least it was getting something right, right? Its equations are often frequently still used, and so it was capturing some sort of structure in the universe, even if it was sort of wrong about there literally being a sea of negative energy, right? Um, okay, so just the last distinction. So the view I've given you is called epistemic structural realism. It says, what can we accept from our theories, right? What is involved in accepting a theory? Can we accept not only that it gets the predictions right, like the constructive empiricist, but also that it's getting the structure of the universe right? You can take a stronger view, which is called ontic structural realism, and that says that's all there is structure. And in that case, you're a deep realist because, um, in a sense, right, if you say that your theory is only talking about structure and all that exists is structure, then you can say science captures everything that's true about the world without ever sort of believing in electrons, right? So that's another view you can have. Uh, but either way, uh, this is sort of where we have to stop, right? The conversation goes on and on. Maybe this is something you want to explore in your paper, although the clock is ticking now on these papers. But you still have time to get a draft in on something on this topic, I think. If you're waiting for week 5 to inspire you for a paper topic, I would encourage you to sort of read ahead because that would be cutting it a little close. Um, but this should this now has taken us as far as we can into this debate, and it goes on and on and on, right? So um, should we be realists, right? That seems to be the intuitive starting point. But geez, how do we know? Who are we to say that right now, at this point in time, we have the right theory, right, of the universe? Seems like probably we'll get better if you have any humility whatsoever. It'll turn out that we were wrong about a lot of stuff. So how can we be realists then? Um, and then we have a few ways to either be empiricist, where you say I'm not a realist, but science is still good for a lot of things, or Worrell, who says we can be a realist about quite a bit, right? About the structure, which is really one of the more important parts, anyways. Okay, so that is it for this week. And next week we'll be moving on to intertheoretic relations, both theory change, right? A very influential view by Kuhn. And then we'll also be talking about intertheoretic reduction, right? So what does it mean to say that physics is like the most basic science, right? And that biology is sort of, it's just particles moving around. So couldn't you just describe biology in terms of physics if you knew everything about physics? Those are the questions we're going to be discussing next week.